Have you ever really stopped to think about what's going on inside your computer? I mean, really think about it? Every single click, every key you press, every file you save, it's all managed by this silent, invisible hero, the operating system. It's kind of like the conductor of a super complex digital orchestra, and today we're going to pull back that curtain and see exactly how it makes the music happen.
Okay, so let's dive right in. Just imagine for a second, you tap the letter A on your keyboard, and poof, the letter A just appears on your screen. It feels totally instant, almost like magic, right? But behind that one simple action is this lightning-fast chain reaction of events. So what's the bridge between you physically pressing a key and the digital result you see? Well, that bridge is the operating system.
You can think of the OS as the master manager of the whole operation. It's the very first program that wakes up when you turn your computer on, and it stays in charge right up until you shut it down. Its entire job is to be the middleman between you and all your apps and the raw hardware. You know, the CPU, the memory, the hard drive. The OS makes sure they all play nicely together and do their parts at exactly the right time.
So what does this manager actually do for you? What can you ask it to do? Well, think of it like going to a great restaurant. You don't need to know how to cook the food yourself. You just look at the menu and place your order. The OS provides a very similar menu of services for all your programs. Let's take a look at what's on offer.
And wow, this menu is packed. Program execution is the big one, of course. That's just loading, running, and closing your apps. But then you get something like I/O operations. That's just a fancy term for input-output, and it's how the OS handles any and all communication with the outside world. We're talking everything from the words you type on your keyboard to the stuff you send to your printer. And file system manipulation? That is the true unsung hero that lets you create folders, save your work, and find it again later, all without you ever needing to know where on the physical disk it's actually stored. The OS handles all this and so much more, from dividing up resources to spotting errors to keeping your data safe.
All right, so we have this incredibly powerful core of the OS. We call it the kernel, that can do all these amazing things. But your web browser or your video game can't just barge into the engine room and start flipping switches. No way. There has to be an official, secure way to ask for these services. And this is where we cross the bridge into the very heart of the system.
A system call is that official request. It's your program politely telling the waiter, "Excuse me, I'd like to save this file, please." The program doesn't actually do the saving itself. It makes a system call, and the OS kernel takes over and does the heavy lifting. I mean, even a simple command in a programming language, like printing text to the screen, is secretly making a right system call to the OS to get the job done.
But here's the thing. Communication isn't just a one-way street. What happens when the hardware needs to get the OS's attention, like right now? That's called an interrupt. When you press a key, the keyboard hardware sends an interrupt signal straight to the CPU. It's literally like the doorbell ringing in the middle of dinner. The CPU has to stop exactly what it's doing, no matter how important, and go answer the door.
And the OS is just incredibly graceful about how it handles this. The split second an interrupt happens, the CPU immediately saves exactly what it was doing. Then it jumps over to a special piece of code, called an interrupt service routine, to handle the request, like, displaying the letter you just typed. Once that's done, it picks up its previous task right where it left off without skipping a single beat. This process is absolutely fundamental to how your computer can do so many things at once.
Now, trying to juggle all of these programs and system calls and interrupts all at the same time, well, that creates a huge demand for storing information. The OS needs a place to keep track of absolutely everything it's doing, which means it has to be an expert memory manager. And that brings us to something called the memory hierarchy.
See, your computer's memory isn't just one big bucket. It's a whole hierarchy. Right at the very top, you have these tiny, ridiculously fast storage spots called registers, which are right inside the CPU itself. Then you have the cache, a little bit slower but bigger. Then comes your main RAM, and finally at the bottom, you have the massive but much slower storage on your hard disk or SSD. And here's the crucial trade-off. The fastest memory is always the smallest, and the biggest memory is always the slowest. The OS's job is to act like a super smart librarian, constantly shuffling the data you need most often onto the fastest, most accessible shelves, the cache and registers, to keep everything running at top speed.
Okay, so now that we have a good idea of what the OS does, let's go even deeper. We're heading right into the engine room now to look at the kernel, the absolute core of the operating system. And it turns out there are a few very different philosophies on how you should build this engine.
So, just to be crystal clear, the kernel is the boss. It's the part of the OS that has total, complete control over everything. It handles managing processes, managing memory. It's the ultimate decision maker for the entire system.
And how this boss is structured, that defines the entire personality of an operating system.
Okay, this table lays out the main design philosophies, and the trade-offs are just fascinating. First, you've got the monolithic kernel. This is what systems like Linux use. The whole idea is, let's put everything into one big, super efficient program for maximum performance. It's perfect for your desktop or server where speed is king. But the trade-off, as you can see in the con column, is risk. One single bad driver can bring the whole system crashing down. Now, contrast that with the microkernel, which is used in ultra-reliable systems, like the software in your car or in a medical device. Here, only the absolute bare essentials are in the kernel, making it incredibly stable and secure. The downside? All those separate parts have to constantly talk to each other, which creates performance overhead. And the layered approach kind of tries to find a middle ground, offering better organization, but again, with its own performance costs.
So, seeing these different kernel designs brings us to the single most important concept in operating systems, period. There is no one perfect way to build one. It all comes down to a fundamental, eternal balancing act.
Every single choice an operating system designer makes is a trade-off. Do you want raw, blistering speed, or do you want bulletproof stability? Do you want something that's easy to change and update, or something that's dead simple and fast? The thing is, you just can't have it all.
And the really crucial point is that these goals are often at war with each other. Just look at performance and security on the chart. If you want maximum performance, you might go with that monolithic design we talked about, but that puts your stability at risk. If you want maximum security, you might add tons of checks and balances, but every single check takes time, chipping away at your performance. Every OS you've ever used, Windows, Mac OS, Android, is a unique answer to the same question. Which of these qualities matters most for what we're trying to do?
And that kind of leaves us with a final thought to chew on. If you were handed the keys to the engine room, what would you build? An OS for a self-driving car where stability is literally life or death? Or maybe one for a supercomputer where raw performance is the only thing that matters? The answer you choose reveals that the invisible conductor isn't just managing our computers. It's really a reflection of our own priorities. Thanks for digging into this with me.